This video is the first in a series that deals with chemical kinetics, the study of rates of chemical reactions and how reaction rates change under varying conditions. In this video, we focus on the definition of reaction rate and we learn how to write expressions of rate from a balanced chemical equation. We have seen in previous videos how we can predict the nature or identity of products of a chemical reaction from a given set of reactants. And we've also seen how we can calculate the amount of product we might expect from a given amount of reactants. Determining the nature and amount of products formed in chemical reactions is obviously of considerable importance in many environmental, industrial, and biochemical applications. However, for most chemical reactions, the rate of formation of products is equally important. Consider 4 everyday chemical processes: the combustion of methane or natural gas, the spoiling of milk, the rusting of iron or steel, and the degradation of plastic in the environment. All of these reactions will take place given the presence of appropriate reactants, but all occur at very different rates, varying from timescales of around a millionth of a second up to hundreds or even thousands of years. From a practical viewpoint, knowledge about the rates of chemical reactions is crucial in food and beverage production, pollution control, drug design, and understanding and manipulating biochemical pathways in medicinal chemistry, as well as in a myriad of other applications. For example, the effect of toxic substances on ecosystems or individual organisms and the effectiveness of pharmaceutical drugs rely just as much on the rate of chemical reactions as they do on whether a chemical reaction takes place in the first place. The study of the rates of chemical reactions is also called chemical kinetics, and it not only involves measuring rates of reaction but also determining how reaction rates change under varying experimental conditions. The reaction rate for a chemical reaction can be defined as the change in concentration of a reactant or product per unit time. The units for the reaction rate are derived from the units for both concentration and time, that is, molarity per second. And since molarity is the moles of solute per litre of solution, we can also express the rate of reaction in terms of moles per litre per second. Let's consider the simplest hypothetical reaction in which a single reactant A is converted to a single product B. This equation tells us that as the reaction proceeds, A is being consumed and B is being produced. And we can plot the course of this reaction using a concentration time plot, where we can see that as A is consumed, its concentration decreases with time, and as B is produced, its concentration increases with time. By convention, we use square brackets around a chemical formula to indicate that we are referring to the concentration of that substance. The rate of reaction for this reaction can be determined from the slope of these curves at any point during the reaction. This is known as the instantaneous rate and is determined by calculating the slope of the tangent of these curves and by considering the change in concentration of a reactant or product divided by the change in time. And we use the Greek capital delta to indicate a change in concentration of B, for example, delta B, and a change in time, delta T. Another important measure of reaction rate that we often want to consider is the initial rate of reaction, which is defined as the instantaneous rate at time t equals 0 and is again determined from the slope of the graph at this time, t equals 0, by dividing the change in concentration by the change in time. A third measure of rate, and probably the most practical to use in experimental settings, is the average rate of reaction between 2 points in time, t1 and t2. Again, we determine the average rate from the change in concentration and the change in time, where in this case, we see that delta B represents the concentration of B at time t2 minus the concentration of B at time t1, and delta T is similarly calculated as t2 minus t1. We can examine the rate of this simplest hypothetical reaction in 2 ways. 1, by monitoring the rate of consumption of the reactant A, or 2, by monitoring the rate of production of the product B. Both are equally valid approaches for determining the reaction rate. And we can write mathematical expressions for both approaches, where we monitor the rate of consumption of the reactant A by quantifying the change in concentration of A with respect to time, or by monitoring the rate of production of product B by quantifying the change in concentration of B with respect to time. Both are equally valid mathematical expressions for the rate of this reaction. In these equations, delta A equals the change in concentration of A, that is, the concentration of A at times T2 minus its concentration at some time T1 earlier in the reaction. Delta B is the change in concentration of B, that is the concentration of B at time T2 minus its concentration at time T1. And delta T equals the change in time, T2 minus T1. You will note the minus sign in the first of these expressions. Rates of reactions are always reported as a positive value. We cannot have a negative rate of reaction. In the case of the disappearance or consumption of a reactant A, the concentration of A decreases with time, and because we calculate the change in concentration by subtracting the concentration at some time earlier in the reaction T1 from the concentration at some time later in the reaction T2, this means that the change in concentration of reactants will always be a negative number, and we therefore use the negative sign to convert the negative delta A value into a positive rate value. So, for the hypothetical reaction of A being transformed to B, where the stoichiometric coefficients of each substance is 1, there are two equally valid expressions for the rate of reaction, one referring to the rate of consumption of the reactant A, and the other referring to the rate of production of the product B. Let's now consider a real reaction where the stoichiometric coefficients have values other than 1. For example, the decomposition of dinitrogen pentoxide to produce nitrogen dioxide and elemental oxygen. We can write the valid expressions for the rate of this reaction by considering both the reactants and products. For example, we can write expressions for the rate of reaction as being equal to the rate of consumption or disappearance of N2O5, or as the rate of production of O2. The problem in this case, however, is that we cannot simply equate these two expressions as we did above, because these expressions are not mathematically equal. If we take into account the ratio of the stoichiometric coefficients, we can see that for every 2 moles of N2O5 that are consumed in a given time period, only 1 mole of O2 is produced. The rate of production of O2 is therefore half the rate of disappearance of N2O5. To equate the rates in this case, we must take into account the stoichiometric coefficients and divide the rate of disappearance of N2O5 by 2, that is, the stoichiometric coefficient of N2O5 in the balanced chemical equation. So we get an expression for the rate being minus 1/2 times the rate of disappearance of N2O5. Remember, the minus sign is present because N2O5 is a reactant. We can also do this for the rate of appearance of NO2, where we can get an equivalent expression for the rate as 1/4 times the rate of appearance of NO2, with the 4 in the fraction coming from the stoichiometric coefficient of NO2. And we can also do it with oxygen, where the stoichiometric coefficient is 1, and therefore the rate of reaction can be written a third way as being equal to 1 times the rate of appearance of O2. In general, for any reaction, A plus B producing C plus D, where the lowercase letters represent the stoichiometric coefficients, we can represent the rate of the reaction in terms of all of the reactants and products by multiplying the rate of disappearance of reactants or the rate of appearance of products by the inverse of the stoichiometric coefficient for each substance in the balanced chemical reaction. And remember, when we do this, we must place a negative sign in front of the terms that represent the reactants.